and we can get started. Okay, so we'll slowly get started. There might be a few more coming, but maybe we can get started now. Okay, so yesterday, where we got to basically talking to tracking detector-based ionization, and we talked a little bit about gas-based detectors, and we saw also how they are a bit of backbones of the muon system in the LHC experiments, because they can cover very large volumes. They can give different compromises of good position resolution or very fast responses. So starting from, I would say, starting from, let's say, Tevatron and other similar experiments, there have been another class of tracking detector that has been developed, and now are a bit of a workhorse for tracking, for charged particle reconstruction, especially close to the interaction point, and are silicon-based detectors. Even for silicon-based detectors, the principle is ionization. So energy lost by ionization detected that type of charge. But the way this is done is a little bit different. Here, you don't have any more gases. You have a semiconductor. And so essentially what you do is to have a PN junction, so a kind of a diode, and then you reverse bias the diode. And this way, basically, it behaves like an insulator. So once the voltage is applied to the two ends, there is, in principle, no current flowing. There is a small amount of current flowing that's called leakage current, but that current is tiny. And so what happens is that because you apply a voltage, then you get some electric field as well throughout the semiconductor. And when a particle goes through, it ionizes the semiconductor and basically causes the electron to shift from the valence band to the conductor band. And these electrons now feel the electric field and then can migrate. Both electrons and the positive ions, so-called holes, migrate and give us a signal. That signal can be read out, similar to what was happening in a gaseous detector. And we talked about gaseous detector that we needed some multiplication. And that actually is also happening a little bit in semiconductor, close to the collection points, through different type of doping that is done around the implant. That multiplication is very limited. So the signal that you get is actually really, really tiny. So what managed, as we will see in a couple of slides, what made possible to use this as detector is to have very sensitive electronics that can read out very small signals. Without that, you can't use this type of detectors. But the principle of sort of at very, very high level is similar when you have a particle ionizing and your electrons and holes drifting. Now, this detector gives you a lot of flexibility in terms of like how you shape this implant where you read out your signal. The first type was so-called a strip type of detector. So you have segments that are very thin and long. Typical distance between one readout and another in LHC experiment, we are talking about 80, 90 microns in between each of the strip. So basically, it can give you a position resolution, which is at the order of like 80 divided by square root of 12 if you don't read out charge. If you read out charge, you can do the same trick as we mentioned last time, which you can look at signal at multiple strips and kind of do a, in quote, weighted average to figure out where the most likely position is. However, because there are strips, you can get very good resolution in one direction, but the strips are pretty long, so you don't get very good resolution in the other direction. So if you want to have both directions, what you can do is to place two of them perpendicular to each other, and then you can get both directions. However, this practically is not the way this is often done, because there is one direction that is usually more important than the other. And so practically what happens is that the two planes are almost parallel, but with just a small angle that typically is of the order of 10 milliradians or so. And that is enough to sort of give some better coordinate on the poorly defined one and increase even better the accuracy towards, let's say, the finely pitched segments. You can also try to go even more and just segment these type of detectors in small squares. And that's what we call pixel detectors. And the techniques to do that got really better and better in years. And now we are at the level that for the high luminosity LHC, we are looking at things like 50 by 50 micrometers square, or even 25 by 100 micrometers square in terms of size. Now, the main problem is that what we saw for the strip detector is that, and the gaseous, is that you had this long strip and you would read out your signal at the end. Now you have many different squares, so you need to read one signal for each of these squares. So how do you do that? Well, at that point, you need to have a dedicated readout electronics, which basically has a single contact for every of these squares. Now, this is a technique which is called bump bonding, which is essentially a very tiny bit of solder of tin that is placed to contact as a contact between your readout chip and every single cell. These type of high density contacts are nowadays relatively standardized in industry. And in fact, this type of techniques is often offloaded from the experiments to be done by industry, but it's still a very niche, very high density, very niche aspect. So there are only a few vendors around the world that actually can perform the connection with the density that we need for these experiments. And you can see an example of that bump bonding. There is actually a picture of how that looks like. It's really a small sphere of tin. And you see the space in between your junction and your readout chip is of the order of a couple of tens of microns. And in fact, a lot of the reliability in producing them is like how many of these connections are breaking, what happens if I have thermal stress, and there is some mismatch in in the material between the two different elements, and then they will contract and expand a little bit differently. That will put stress into these bonds and they can break them. So there is a lot of work that goes on into managing these type of stresses and making sure the design is such that this connection stays stable for the duration of the experiment. And after you've done that, your readout chip needs also to ship out the signal. And so that is usually done with this bottom part where the signal is processed inside the chip. And basically then there are small pads where very tiny wires are used to connect to a print circuit board that then ships out the signal from the detector. And this is really a very delicate process. And this bump bonding in particular is really the most delicate part of this production. I will just briefly mention that one thing that what I describe is what is called a hybrid pixel module, because it puts together two different elements. This PN junction, what we call the sensor that will be biased, and then a dedicated chip that is used to read out the signals, okay? And since I mentioned that the connection between the two is a critical element, you might wonder, well, can you just make them together from the start? And that's the idea behind the monolithic sensors, and where essentially the readout electronic and the sensor are just designed together in the same piece of silicon, okay? They chemically grown to basically to do what we need, and all the traces for the chip, readout chip, and the electronics is that put on the same wafer of silicon. This is great because it's a single process, easier, cheaper, and actually can give us even better density because we don't have to put individual solder bumps to connect the two. So why we are not just using that? This will take me to a tangent, but the main problem is that this type of chip, until let's say very recently, is much more subject to radiation damage. So the radiation from, for instance, LHC environment is much easier to create damage to this type of device than it is for hybrid ones. We can make the hybrid ones way more robust against radiation damage. For that reason, in fact, this has been a choice for Alice in their tracker, where they are expecting less radiation than experiments like CMS or Atlas. And so for them, this has been a natural choice for their upgrade. And this actually was considered also in Atlas for the external layer of the tracker, but then it was not proven in time that it was enough radiation resistance. Okay, so we mentioned about signal readout, and when you talk about silicon detector, there are a couple of numbers that if you remember or if you know easily how to find, they will make your life much easier to understand how to dimension a detector like this, or just to have an idea what you need to read out. And in particular, basically, to create in this type of doped silicon junction, an electron hole pair, so to have the electron have enough energy to jump into the conductor band, you need about 3.6 electron volt. And if you need to remember one number, is that the typical ionization for a particle which is in the minimum ionizing particle regime that we saw yesterday in the Bethen-Bloch formula is about 80 electron per micrometers, okay? So the thickness of these devices is of the order of about 100 micrometers, which basically means that you get around 8,000 electrons from a particle that is minimum ionizing and traverses your sensor straight up. Okay, then of course, if it has an angle, it will deposit a bit more. If it goes towards multiple pixels, it will share the charge and so on. But that gives you the order of magnitude. So 8,000 electrons is the order of femtocoulomb. That's a tiny charge. And so for doing that, as I mentioned, what you need is really a very sensitive electronic that can take that small signal, that can amplify it, and in some way digitize it to give you the information outside. And so the way this signal is digitized is through a technique which is called time over threshold, which is often abbreviated TOT, and very often people forget to spell that acronym out. So you might see it very often used by people without spelling it out. And the idea behind it is that once you basically, you have amplified your signal, instead of trying to integrate that signal and give you the overall charge, you basically count, you have a threshold and you count for how long the signal stays above threshold. And so you basically, you have some clock cycles and you count how many clock cycles the signal stays above threshold. And you can relate that to the charge that was deposited. So that gives you an idea of like how much charge was deposited. To give you an idea for the luminosity LHC, this is what we'll be doing it. If instead you want to only read out if there was a signal or not, you just read out if the signal was above threshold or not. That's what we call binary readout. And then if instead you actually count how many clocks the signal was above threshold, that's what we call time over threshold. And to give an idea for Atlas and CMS, the time over threshold has a resolution of 4 bits. So you have 16 values possible. And the clock where we count is actually the 40 megahertz, 25 nanosecond steps LHC clocks, which also tell you that basically it will tell, it can take up to a couple of hundreds of nanoseconds to be able to read out the signal, which means also the pixel is in quote busy for a couple of hundred nanoseconds from when one signal arrives to when it's ready to record a new one. And that's why you need high density, because we have collision every 25 nanoseconds. So you want the probability of multiple particles hitting the same pixel within this 100 nanosecond window to be very small. And so this detector are designed such that the typical occupancy, so the probability of a particle hitting a pixel, is of the order of 1% or so. So that the probability of having multiple particles hitting the same pixel within this window is rather small. Okay, so in practice, these tiny things are assembled in giant structures and in an almost hermetic design. So this is a picture of how the inner tracker for the high luminosity LHC for the Atlas will look like. So essentially what you can see is essentially a central part. So this is a cutout. You have a central part which is made of barrel-like structure. And then to close, to make it hermetic, you have these sort of rings at the side. So we can see maybe like this a little bit better. But you can see basically you have all these different sensors placed on carbon structure that will take them. And then you have this ring-like structure that are designed again with carbon foam that needs to be also cooled, and where you need to bring power and data in and out. What you will most likely sometimes see is this type of diagrams, which is just a schematic view where you can see the radials and Z, which is the axis of the beamline. You can see essentially where the different sensitive layers are placed to. And so the technology is what we talked about. There are pixel type of detector in the innermost region where you need the most granularity, and strip light detector where you need to start covering larger and larger areas. And what you can see also is the coverage of this detector, which tries to be pretty hermetic. So if you note the scale, this is 3 meters, and then basically is as large as 1 meter high in radius. And then so the straight line in this type of diagram, these are basically cylinders. And then the vertical line are these rings around that we saw before. Okay, so you often will see these diagrams. It's sometimes nice to relate this to how this actually looks in practice, which is more something like that. One aspect that I wanted to highlight, which has been a quite large effort in optimizing, is like how close to the interaction point you can get. And so we get to about a bit more than 3 centimeters from the interaction point, which is just outside the beam pipe. And then, okay, yes. Before showing you the analogous CMS one, I wanted to show another concept that actually CMS is going to use in their high luminosity LHC upgrade, which is so-called double layer. So we saw this pixel and strips detector. What you can do is actually make a sandwich between them and have them relatively close by to each other. And then having essentially a single readout chip that tries to read both. Now, if you want to do that, you cannot have the same type of granularity for the pixel detector. They're using so-called macro pixels that are a bit larger, and then a strip detector. And why would you want to do that? The reason is basically that for a particle going to the interaction point, if you have 2 layers very close by, you can try to distinguish if a particle was going straight up, so had a relatively large momentum, or if the particle has a relatively low momentum and because of the magnetic field is essentially curving. So to do that, you of course need to assume that essentially the particle is coming around the interaction point, or need to essentially do special attention, special things for that. But in this way, directly from the readout chip, you can essentially try to correlate the signal between the 2 layers and figure out if you're seeing a signal that is probably coming from high momentum particle, or if you're seeing a signal that is coming likely for a low momentum particle. And you can do that very quickly. And for that reason, we'll see later in the lecture, this morning, this can give a fast signal that can be used actually to analyze very quickly the event already at the trigger level. And this is actually a rather nice piece, but also a very complex piece to assemble. And so down you can see how that practically looks like. And you see all the electronics around, and then the sensors basically at the center. And then what you don't see is the other sensor at the bottom of it. And so this actually will be used in CMS for the luminosity LHC. So this is a similar schematic. You see here 3 different technologies. So at the outermost, again, you have strip detectors, which is needed to cover the large areas. Then in the middle, in blue, you see again a central barrel-like structure. Then you see that ring, and then you see an intermediate part where sensors are slightly inclined. And we'll come to that in a second. And that is basically the outer tracker is where they also use these double layers, or even called PT module, because of their ability to distinguish different momentum of the particle using this sort of macro pixel and strip detector. And then the inner tracker in green and orange is based essentially on pixel-based detectors with the highest granularity we can get, which is this 50 by 50 or 25 by 100 micrometers square. So now, let's see, any of you have any idea why you would incline those modules in those regions and not just make them straight? Any guess? Okay, so we'll get to that in a minute, but essentially is actually wants to minimize the amount of material the particle traverses when being detected. So if you think about most of the particle coming from the interaction point, you see that this module essentially facing towards the interaction point, so that given a thickness, the particle will more likely hit them almost straight up, okay? In fact, it would take us too much in a tangent, but if you're curious in a coffee break, I can explain you why the optimal position of this module is that a particle doesn't actually hit them completely perpendicular, but at a small angle. That becomes the most optimal one. And there are a couple of reasons for that. But okay, let me then go back. So now that we've seen this type of silicon detectors and we've seen gaseous detectors, let me go back to charged particle reconstruction. And when we started this, I was mentioning that the goal of charged particle reconstruction is to identify how many electrical charged particles were produced and measure the kinematic properties. And then we also mentioned that how we want to sort of measure a minimal interaction of this particle with our detector. And now we've seen what detectors we can use. And this will give us a set of points. And we try to be as hermetic as possible, as shown by the sort of the sketches of the detector I showed. Then we have a uniform magnetic field that will create an approximately helicoidal trajectory. And then the only thing left to do is to design an algorithm that basically fits an helix along these points. And then here, I also wanted to introduce a little bit that being a helix, what you can describe the trajectory, you need 5 parameters. And the most common convention that you will see around is to use a combination of these type of 5 parameters, where starting on the right, you have the charge over the momentum or charge over transverse momentum. You have the theta angle. So here is the angle between the z-axis, which is the one parallel to the beam pipe, and the radial direction. And then you have phi angle, which is defined in the transverse plane. And then you have D0 and Z0. I'll define them a little bit later, but this basically are a measurement of how close to a reference point, which usually is the center of the interaction region, your trajectory is basically coming close to. The other formula that we saw already when talking about accelerator, which is very useful to remember here, is what relates the momentum and the radius of curvature. So if you want to know, for instance, and that magic 0.3 conversion factor, which is very useful to relate this quantity in meter GV and Tesla. So for instance, if you want to know for a 2 Tesla magnetic field that we have in Atlas, what's the minimum momentum of a particle such that it will not curve around, but it will get into the calorimeter, which is a meter away from the interaction region, you can easily use this formula and figure out that you need at least about 400, 500 MeV to be able to get to the 400 MeV to get to the calorimeter. And with a momentum less than that, the particle will just curve earlier and go back, okay? So that's a very formula to use. So I wanted to talk a little bit about charged particle reconstruction. One, because I find it a fascinating one. Another reason is because, as we've seen at the beginning, when I motivated, it's actually one of the most CPU consuming part of our event reconstruction. And so this is how more realistic events look like, where in the upper left, you can see of the order of 50 particles produced, and you see the points in gray, which of course coming from the particle, but can come also from noise, can come from radioactivity and excitation of material that has happened previously in other collision, and then with a different time scale, you have decays. And so this will give you a set of points and you to find those trajectories. That seems still not an impossible task. Then you see what happens when you have 500 of them. And then at the bottom, you see how that looks like when we have 5,000, which looks much more similar to what we'll have in the high luminosity LHC. So that's the bottom right is basically what we'll have to deal with. And then for each trajectory at that point, we will have around 10 to 15 points. But as I mentioned, only about 10% of them will actually end up in trajectories. So not every point is actually used or gives rise to trajectories. So the most naive assumption you can say, you say, great, I have a charged particle propagating in vacuum in a homogeneous magnetic field. That's a helix. So it's actually, I know how to describe the helix. I can just match helix through all the points, take into account their uncertainty, I should be done. And it's actually, if that was the case, it's not a very hard problem. We know how to do it. We know how to do it pretty well. So what makes it hard? And it makes it hard, the fact that all these approximations that I mentioned there are actually broken, and we have to take those into account. So for instance, let me actually state, the magnetic field is actually not uniform to the accuracy we need. The magnetic field has been mapped, believe me, has been mapped at the beginning of the LHC, before we installed trackers, when everything else was in place, the solenoid was turned on, and they went and mapped 10,000 points around the solenoid to figure out how the magnetic field looked like. And that map is still used nowadays to see how non-homogeneous the field is. The detector elements may not be in the exact position we intended them to be. And given we're talking about micrometers, it's impossible mechanically to ensure the detector will be in that position at the micrometer level. So we need techniques to figure out where the detector actually is. And that also moves with time. And then in addition to that, we have more physics effects. So we talked about ionization loss. So the particle will lose a little bit of energy when going through, but I will show you a little, and I'll go through this effect. We have other physics effects which actually makes the trajectory not a perfect helix. In fact, what we basically can say is only locally speaking, the trajectory will be helicoidal, but the overall trajectory is actually very firm for a nice and beautiful helix. To add to all of this, we also have the problem that we need this algorithm to actually run fast. And to give an idea, for real-time event analysis, we need this algorithm to run in a few milliseconds, hundreds of milliseconds per event. And for offline reconstruction, we need them to run of the order of 10 seconds per event to figure out all these trajectories. Okay, so let me start with multiple scattering. So when a charged particle traverses a medium, some material, we talked about the Coulomb interaction that also causes ionization, but that interaction will also deviate the trajectory of the particle, okay? And practically speaking, you will have a zigzag sort of trajectory along the material. And so the angle the particle sort of will enter the material is actually different from the angle with respect to a surface that the particle will exit the material. And that difference in angle is actually can be described as a Gaussian distribution. And the width of that Gaussian distribution depends basically on the formula below. You see that depends on the momentum, depends on the charge, and depends on this x over x0. We'll come to that in a second, but that is essentially a measurement of the thickness and the material that, that you're traversing. It's not only the thickness, it's also the material properties of the material. And that's what is called radiation length. And we'll see this a little bit more. In addition to that, we have other effects. One of them is called Bremsstrahlung, and we've seen this a little bit. So is when a particle going through the material will interact with the Coulomb field of the atom and can radiate a photon. And so the energy loss that you lose by radiating can be related again to the property of the atom and to energy and the mass of the particle. And this is basically proportional to the energy of the incoming particle, but is inversely proportional to the square of the mass. So that's why sort of you will often hear Bremsstrahlung as associated to electrons. It's just because of these inverse square mass proportionality. So for electrons that are relatively light for the particles we are looking at the LHC, we are producing at the LHC, this effect is much larger than for other particles. It happens for all charged particles, but because of this dependence is mostly important for electrons. And so the energy that we lose by Bremsstrahlung per unit length is actually related to its proportion to the energy, and the proportionality constant is what is called radiation length. And so this basically means that the energy that the particle loses as it goes through the material is basically an exponential function, is function of the thickness and this radiation length of the material. Similar, the mean distance over which this electron loses like all but 1 over E of its energy is defined, is basically, yeah, is really what defines this radiation length in terms of x0. It's pretty obvious from the formula. And in addition to that, since the particle will also lose energy through ionization, you might wonder how the two compare to each other. And so you can see that basically from the bottom right plot, where you see the energy loss, the energy and the energy loss as function of the energy loss by Bremsstrahlung ionization. So when you start from a particle with some energy, will start losing energy, so its energy will go down. And so there will be a point where sort of from predominantly losing energy through Bremsstrahlung, now the particle will start losing energy by ionization. And that turning point, that point is called the critical energy. And so to give an idea, electrons in iron, that critical energy is around 20 MeV, and for muons is around 1 TeV. That's because of that inverse square mass dependence. And this critical energy will come back as a concept in a few slides when we talk about calorimeters as well. But it's also important for trackers. Okay. Finally, the third physics mechanism I had listed is the nuclear interactions. This is where essentially a particle interacts with the nucleus of the atom. So now we're not talking anymore interacting through the Coulomb force with the electron cloud, but we are talking about interacting with the nucleus. You can have a head-on collision. And so in this situation, the original particle is essentially lost. And what you have is basically a fragment of hadrons that gets produced. Someone is, okay, looks good. That gets produced by this impact. You can try to describe the probability of such interaction happening in a very similar way. So the absorption of hadrons is described in a similar way, where in this case, we have like from a flux of hadrons, the number of hadrons, how many, from a starting number of hadrons and 0, how many they survive after some length. And you have a similar formula where now instead of radiation length, you have this lambda I. And this lambda I is basically the mean free path for hadrons in a material to interact, and is called nuclear interaction length. And this type of property is mapped for material, is measured for material. I should have put a link here, but basically if you go to the pdg.lbl.gov, the particle data group, you have full of tables, and there is one link which is called nuclear properties, which might not seem very appealing, but actually contains all these different numbers. If you need any back on the envelope estimate, you can find them all there, both from simple elements as well as compounds. That's a very useful resource to have. Okay, so how these things play together. So when we have to, so these basically things make the job of finding this trajectory significantly harder. But by itself, I've just went through, we have a mathematical model to describe statistically how they change the trajectory, or what is the probability that the trajectory, that the particle will deviate by some angle, will undergo hadronic interaction, will emit Bremsstrahlung and again lose energy. So we can describe them mathematically pretty well. And so this model is used basically for propagating a trajectory through the detector with a model of the detector and figuring out as we go through how much material we traverse and what is the probability of these effects of occurring and how they modify the trajectory. And you can literally create a probability or a chi-square that basically tells you how compatible it is, how likely, how realistic a trajectory that connects n different points is when taking these effects into account. So this basically gives us our foundation, our mathematical model that given a set of points, I can tell you this is unlikely to be a realistic particle, or yes, this is compatible for a particle that goes through this amount of material and scatters around. So I can really build sort of a likelihood or a chi-square that gives me how likely is to see this type of deviation from a perfect helix. And yeah, this is basically what it does. This delta M is basically the measured position versus what you expect from a perfect trajectory. And that second term is basically telling you the deviation of this part of the perfect helicoidal parameter from what you measure to what they should be. Yes. That G is just the uncertainty, the intrinsic uncertainty on the measurement itself. And then in the second term instead is basically the uncertainty on, is just the how much, the sigma of that effects. We were talking about like multiple scattering as a Gaussian distribution, and I know how to compute that sigma. That goes what in the second term. And the first one is the intrinsic resolution of the measurements. And it's actually, I mentioned before, it's a whole very interesting topic. How do we assign, how well do we know the uncertainty from like a pixel detector and strip detector is actually slightly non-trivial, but I don't have the time to go there. In case in a coffee break, I'll be happy to elaborate on that. Okay, I actually gave that problem to graduate students during one class about how to determine the best position and see what algorithms they could find to do that. And you wouldn't believe how complicated they managed to make it. So I was pretty impressed. It was very nice. Okay, so now we have a mathematical model. We know these type of things, but still we missed one part, which is sort of, I have points, now I need to start grouping those points, cluster those points in possible trajectories, that then I can evaluate with this model if they are viable trajectories or not. So how do I make these points? We are talking about tens of thousands, hundreds of thousands of points. I cannot just make every single combination. That would be just enormous. Okay, and so there are two different classes of approaches that I like to categorize for algorithms that cluster together this point to find trajectories. One is called global approaches. One, I would say, is the global approaches, which can have either global transformation or machine learning enable algorithms. And I'll just show you an example. Or the second one is more local sequential approaches, which they work, well, we'll see a little bit. They're like tree-like algorithms where we try to connect points after point and navigate through our detector. And I'll show you in a second. So this global, one example of global transformation is probably one of the first tracking algorithms in sort of serious tracking detectors is what is called half transform. This basically is just a way in which you transform the coordinates of your point. So you work on the transverse coordinate, which is the one where you expect a circle from the helix. And then what you do, you just do a coordinate transformation. You go from that XY space to a UV space. What is the property of this transformation is that a circle in the XY space will essentially be a point in this UV space. Okay, and a point in XY is then mapped to a line in this UV space. So I can take every single point and that you see these three different colors and that becomes a line. And then the problem becomes find the intersections of this line. And that point in UV, I can map back to that circle in the XY and that's my trajectory, which is brilliant. Now, what's the problem, practically speaking, is that when you do that, practically you need to discretize your space. You often end up with like, when you have high density fluctuation of global and local maxima that you need to distinguish if it is really two different charged particles or not. And practically speaking, when the density becomes very high, it's actually very difficult to make this work. However, they are very fast. And in fact, they actually are being considered for some very fast algorithm that we need to do real-time track reconstruction, even at the luminosity LHC, with limited accuracy. Similar for global transformation, more recently, people have been investigating very hard graph neural networks. And then these are basically are neural networks that connect different, that creates graph and give weights to the connection and to the points of each of these graph. And the practical implication sort of, and what your idea is basically to have single points in your detector be nodes in this network. And then the connection between them represents how likely they are coming from the same trajectory. And then you want to basically train an algorithm to recognize what are the most likely connection. And in principle, you can think, I mean, there should be a lot of computer science around it, because it's also when you put on Google Maps, I want to go there, what's the best trajectory, needs to connect various points and find the best path. Just the metric here is different. So these have potentially very good parallelization in scaling. But in my opinion, they're basically at this point just past the conceptual stage. So they work well in idealistic models. In realistic scenarios, there is still a significant amount of work to do, and it's a very active research area. It's very rapidly evolving. If you just search on arXiv GNN tracking, you will start seeing how many papers are coming out on this topic. The workhorse, or what we use currently, the LHC, and are planning to use, is what we call these local type approaches, which work a little bit like a chess engine, if any of you is familiar with that, in which you need to evaluate, in a chess engine, you need to evaluate what possible moves are, and you want to look further and further, what's the implication of the next move, and then the next move. In this situation, the move is just the different points in the different layer of our tracking detector. You want to know which trajectory connect possible points. And now this is a combinatorial that can explode very quickly. And like in chess, the trick is basically to prune some of these branches as early as possible. So discarding moves that are not very good as early as possible. And so similar here, we want to discard trajectory that are not very likely as early as possible. And as we move from one layer to another, we have a model that tells us how we propagate through. And then we can figure out if there is one or more points that are compatible with possible trajectory and split in possible candidates. And then we evaluate these candidates and figure out in the end a unique set of trajectories. And this is really the workhorse of how we do tracking nowadays at the LHC. More realistically, it's actually slightly more complicated. We often have a pre-processing stage. We have this so-called combinatorial Kalman filter, which is this iterative process a la chess engine that goes through and build track candidates using a Kalman filter approach that simply allows us to update the trajectory parameters easily, adding or removing measurements. And then we have a stage where when we have this initial set of candidates, we go through them again and clean it up and figure out if there are duplicate candidates, if there are candidates that should be kept or removed, and then add them to the final track collection. And in fact, we often end up doing this cycle multiple times. So very often we can tune these algorithms to be specifically looking for some particular type of trajectories. And this is what you see in this type of plot from CMS, which shows the tracking efficiency. We'll come to that in a bit, but the probability of reconstructing a charged particle versus the simulated tracking PT. And you see various different colors. Each of these colors is a dedicated step where basically we find trajectory, remove the hits of the points that we used, and then rerun those algorithms with different setups. And in this way, we basically, for instance, look at specifically lower PT particle that might be slightly displaced, particle that might only live up to the pixel detector, and so on and so forth. And all of these things are really extremely optimized code for the specific usage. So we talked about tracking reconstruction efficiency. So I wanted to just show you qualitatively why plots of tracking reconstruction efficiency look like this. So here you see an example of the expected efficiency that we'll have for tracking at the HL-LHC for 3 different types of particles: muon, electrons, and pions. So it would be nice to quiz you on why that is different, but the answer is written on the slide, so maybe not be very helpful. But the point that you see for muons, actually, the amount of multiple scattering, etc., is relatively small. And our efficiency is purely determined by how well our algorithms do in reconstructing those trajectories. And you see that efficiency is very, very close to 1. Our algorithms work very well. But then if you look at hadrons like pions, you see the efficiency has an actual shape and is far from 100%. The reason for that is because pion undergo hadronic interactions with nucleus of the matter. The cross-section is higher for the others. And therefore, and that was limit our efficiency. If the particle undergoes hadronic interaction too early on, it doesn't deposit enough points for us to reconstruct a trajectory. And that's also why we want to make our detector as light as possible to lower the probability of hadronic interaction happening early on and not giving us enough point to reconstruct the charged particle. And so in fact, you can basically map on the right, you can actually see the profile of how much material in radiation length, or I probably should have put the hadronic interaction length, is as function of the angle, in this case, eta, which, yeah, with the same there. So you see that most of our material is concentrated in the forward region when seen in a light of sight. And basically this shapes the way that our tracking efficiency looks like. And then for electrons, they should behave in some sense like muons. But you see that actually they behave a little bit more like pions. And the reason for that is Bremsstrahlung that becomes important because electrons are very light. And Bremsstrahlung is also dependent on the amount of material, and therefore they follow a similar shape as in the case of pions. Okay. Then you can wonder how well we measure the kinematic properties of this particle once we reconstructed them. And so in particular, the momentum resolution depends on the magnetic field strength. The higher it is, the better we can do. The length of the tracker, the measurement resolution itself, of course, the better we measure, the better the trajectory is determined. And the number of measurements you have is the amount of material in the detector because of the multiple scattering component, which doesn't give us a perfect helix. You can create easily a toy model that estimates from n measurements what is your expected track resolution, and you end up with a formula like the one above, which I find it useful for many of like simple toy studies. And this formula is essentially two pieces. One that determines, the first one that determines the resolution due to simply having n measurement with some uncertainty in a magnetic field, and the second piece which takes into account the contribution of multiple scattering. And so you can see an example. I will just go through this right plot. So you see an example of how these two pieces combine together versus the PT of the particle, and that's the resolution of the momentum over the PT. And you see that you have a multiple scattering component that is sort of flat here, and then your intrinsic estimate that goes up. So basically, at low momentum, you're actually often dominated by the multiple scattering component. And the intrinsic resolution is what dominates the momentum resolution for higher transverse momentum charged particles. That's the rule of thumb to, sort of, for LHC detector to keep in mind. In addition to momentum, we often want to know if a particle was coming from the interaction point or if it was coming from some other particle that was produced at interaction point and then decays. And the way we do it is looking at variables like these impact parameters that I mentioned before. So here you can see the definition a little bit better on this right plot. If I have a trajectory and extrapolate the trajectory through my helicoidal, my helix trajectory, I can see if that helix intersects my interaction point or if it gets close but not quite touch it. And then once you do that in the transverse plane, the minimum distance of your trajectory to that point is what we call transverse impact parameter. And then from that point, you can measure also the distance in the longitudinal plane, and that's called the longitudinal impact parameter. I put down, I will not go through, you can also create toy models to see how much, given a set of measurement, your resolution on that quantity will be. And so that's a useful toy model to have. So that's, I put it here more reference. But the whole point is that it contains an intrinsic resolution part term and a part that depends on the multiple scattering as well. Yes? What is? Angle T. Five up there. Oh, it's just the angle, is the projection of that momentum in the transverse plane, and that is the angle between the momentum and the axis. So it's just the phi of that particle. It's really just very confusing from this. It's not different from this definition of phi. In the transverse plane, it's just the angle between the momentum and it's just that in this 3D representation, it seems kind of up in the air, but it's actually that PT, you see that vector, is the projection of the momentum in the transverse plane, just to define that phi.
The picture.
Yeah. It seemed a bit confusing from that picture. One day I should make a better picture. It's actually, this is by far the best picture of definition of this I've ever found, which tells you a lot about it. Okay. And so similar using tracks, we can then look at points where charged particles were produced. So that's what we call vertex. And then we have either what we call primary vertices, so primary interaction, like main proton-proton interaction that give rise to multiple particles. But we can also have particles that actually fly for some distance and then decay to other particles. That's what we call secondary vertices. And that becomes very important for like relatively long-lived particles, for instance, hadrons that contain big quarks. So those will tend to fly for some distance of the order 100 microns. It can be also millimeters and so on, and depending on how their momentum is. And so reconstructing, then they decay into charge and neutral particles. So being able to find charged particles that actually come from a point that is slightly displaced is a great way to identify if you have produced B hadrons that you don't see directly because they decay, but you can see the decay products. More practically, the modern way to identify these hadrons is actually to use a combination of these impact parameters, secondary vertex reconstruction, and many other variables, and put them together to find basically all the possible correlation they might have. And so this is an example. The upper left is one of these discriminants. This is just the invariant mass of a secondary vertex that's reconstructed. So you just compute the invariant mass of particles. But on the right, you see basically the output or a more sophisticated tagger, which combined through machine learning various different observable. And the way we nowadays train these taggers is like we try to differentiate at the same time heavy flavor like from B hadron, C hadron that have a slightly different lifetime and slightly different kinematic, or particle produced from light hadrons that just immediately decay, immediately hadronize to hadrons at the interaction point, but you might mistake for a B hadron and so on just due to resolution of the measurements. And so all the information is put together, and you often will see this type of plot which characterize the performance of this algorithm as a function of the efficiency you want to isolate, in this case, for instance, B hadrons, and the probability of instead of having a light flavor or a C jet misidentified as a B hadron. Okay, and this really offers the highest discrimination, and the big effort here is how to make these discriminants robust against your knowledge of the simulation of how these things go, of how these things decay, or how your detector is made. And one simple thing, and it seems you can think about a lot of very complicated problems there. Sometimes even the easiest one are actually limiting us. And I can think about sort of even a few years ago where we found that in most of our simulation, just the probability of B hadron decaying to specific final state, which is very well measured, is tabulated in the particle data group. Actually, every simulation, every generator that puts that is sourcing that information from the particle data group in different ways, because there was no automatic way to grab that information. And each script that they used to source it had different bugs. And most of those generators have actually the wrong fractions. And this causes basically this discriminator to then not behave very well when applied to data, just because those fractions were completely wrong. So that's sort of something you can easily end up messing up. And this type of flavor is then important for measuring, like when we look at Higgs decays, for instance, to charm quarks, and we need to differentiate if we are looking at charm-based hadrons versus B flavors or versus light quarks. And this is just an example of a projection for high luminosity LHC, where you can see that even with all the luminosity we'll get, this will be a very hard signal. The red line is the expected signal times 300. And then the different colors represent different type of background. And in particular, the blue ones are sort of the different shade of like blue, for instance, are heavy flavor, or when I have a light and maybe a charm quark, or a light flavor in the final state. Yeah, I will not say more about this part. Okay, so we were drifting already a little bit towards sort of how I identify what type of particle am I reconstructing. And at the beginning, when we started talking about detector and charge and particle reconstruction, we went through, this way, correlating the tracker with the calorimeter, I can say this is an electron or a photon and so on. But sometimes, that categorization stopped short when I said, okay, this can be a hadron. But sometimes I need to know what hadron was produced. Was that a pion? Was that a kaon? Or something else? And then this is very useful in some situations. This is an example of a B+ reconstruction, I think from LHCb, but doesn't matter, where you want to basically isolate the case where you had a kaon. And then if you just reconstruct without knowing if your particle is a pion or a kaon, that's the type of a signal of the background you get on the left, where the big blue part is parts where sort of you are actually having a pion in the final state, and then the red part is the signal with the kaon you're trying to reconstruct. So if I could get some amount of discrimination between pion and kaon, and we'll see in a second how, I actually can transform the thing on the left to what is on the right, where I enhance the kaon and suppress the pion, and I can isolate that type of signal. So how do we do that? And actually, we go back to something we've seen, which is energy lost by ionization. And in fact, because at relatively low momentum, because the energy lost by ionization depends on the velocity of the particle, and because I measured the momentum, through the tracker, different masses will correspond to different velocities. And so this essentially can offer us a measurement of the energy loss, can offer by ionization, can offer discrimination between hadrons that are, for instance, pions and kaon that have different masses. And so the left, you see how well we can do this in time projection chambers. We didn't have a chance to talk much about that part. It's a gaseous detector as well. And then you can see essentially versus the momentum of the particle, the energy loss by ionization measured by this detector. And you see different bands, and these stripes are just the 1/β² dependence of the ionization loss versus beta gamma versus the velocity. Okay, so, and the different particle species, because they have different masses for a given momentum, they have different velocities, and therefore different beta gamma, and therefore different ionization loss. So from that measure, you can tell essentially some separation between pion and kaon. And even a pixel detector has much less resolution, but you can still use it to differentiate at relatively low momentum pion and kaon. What you can see immediately, however, is that as soon as the momentum becomes higher than a few GeV, they all enter in this minimum ionizing particle regime. And so regardless the momentum, the beta gamma value, as soon as it is above about 3, their energy loss is relatively flat. Okay, and so this discrimination power is lost. So it's only useful at very low momentum. Okay. However, this can actually be used directly, even in direct searches for new physics. This is one example where we look for new particles that might be very heavy. So what happens if you have a particle which is as heavy as 1 TeV, 2 TeV? At that point, those particles are so heavy that actually they will not be relativistic, and their velocity is significantly lower, and therefore they will not be minimum ionizing particles. And so we can use the DDX to actually tell apart most, I said, the particles with high, all the particles, standard model particle with high momentum at LHC will be minimum ionizing. And we can use DDX to tell apart if there is a very massive particle charge that was produced and is just producing an excessive ionization energy loss. And this is something we use to set limits on, for instance, very high mass SUSY particles or other exotic particles that could be produced. Okay, there is other ways we can also identify particles. One way is the Cherenkov radiation. So this essentially comes from a charged particle traversing the medium and polarizing the medium around it. And then you can figure out basically how the electric field of this medium reacts. And once the particle is above some threshold, these waves of electric field actually become do constructive interference, and they create really a cone of light. And that only happens, and the angle of that cone of light is directly linked to the velocity of the particle and the diffraction index of the medium. So that basically is telling you immediately, if I see a light in a cone when traversing that medium, I can detect that light, the angle of that cone is directly linked to the velocity of the particle. And so similar as for the energy loss, I can use it to identify particles that have different, I can have the momentum, velocity that can give me a mass. And so that I can basically identify what type of particle I'm looking at. Yes, and this is the concept used, for instance, in the rich detector at the LHCb, where actually you can see basically how that looks like. There are different actually type of media that are used to create Cherenkov radiation. Then radiation is deflected, and then there are particular photon detectors that collect this light and make images like the one on the left. The one on the left is actually a pretty cleaned up image. It's usually more messy, but after cleanup, you end up with this sort of cone of lights that are seen as circles in this plane. And then finding these circles allows you to then match it to what was the angle of this cone, and then can give you a measurement of the velocity of the particle. The nice thing of this is that now here we can get pion cone separation to much higher momenta. This works great from about 1 to 100 GeV. So when you need particle discrimination for higher momenta, this is a much better way to go than the energy loss as an identification for particles. Last but not least, we can actually measure directly the velocity with just a stopwatch, just doing time of flight measurement. And if you have a reference time and a time of arrival, we can just try to measure how fast the particle was traveling. This can be, you need, of course, very sensitive timing detectors. And then once you have that, you can just relate the difference in velocity to, for instance, if you have two different particles with two different masses, you can compute what is the difference in time. And that can give you immediately an idea that if you want to have some useful discrimination power, what is the type of resolution in timing that you need. Note that to be able to do that, you need two time measurements, the starting time and the end time, okay? And very often when you have a detector, you will have a particle arriving to that detector, and that will give you end time, and then you need start time. And that start time is usually taken using particle that we know that most particles will be minimum ionizing, will be very close to the speed of light. And so using the time of those particles and the speed of light, we can find out the reference time, the beginning reference time. And then for a particular particle, we are testing if has a slower velocity than speed of light, we can use that timing difference to figure out exactly that velocity. And in fact, this timing, timing detectors is actually a very hot topic in terms of R&D and development. It will play a very crucial role in some of the luminosity LHC upgrades, as well as we know that it will play a fundamental role in any future collider, in detectors in future collider. There are a huge variety of timing detector and technologies that are being developed now. It's a very, very active field of development. I will mention just one and give you some just general concept for this. This is the so-called low-gain avalanche detector. It's also a silicon-based detector, which has a similar concept where by ionization, you create an electron hole pair and you measure the time of arrival. What's different from the silicon detector? You want to make this time of arrival measurement as accurate as possible. So usually you use very thin sensor. You end up using electronic that is dedicated to this type of readout. And the reason for that is because if you want to summarize what are the main effects that enter your time resolution, the first one is what is often called the Landau term, which is just the fact that as the particle ionizes your material, where exactly these electron holes are created is a stochastic phenomena. They will not be always at the same place. So depending if they are created earlier or later, when your signal will actually arrive to your detector will be slightly different time. That seems a tiny effect. This is often the dominant effect in timing resolution for these detectors. Then again, to measure a time, you need a reference clock. Okay, and to give an idea, even the reference clock distributed by the LHC is actually keeps sort of floating a little bit around. That's called jitter. And that's at the level of 5 picoseconds for the LHC clock. And then you need to digitize that time. And that electronic also introduces noise. And that's this TDC part. And then finally, you have the fact that the more charge you have, the steeper is the rise the signal. And so if I have a threshold, I don't have any more. Okay, fine. If I have a threshold, let's see, it's a small thing, but if I'm asking when, like a voltage and time, if I have a small charge, that will probably do something like this and go down. If I have a large charge, that will do something like that. And so you see that the time, while the particle arrive at the same time, the time the signal passes the threshold changes depending on how much ionization loss I had. And that's what basically is called the time walk effect, okay? And these are sort of your guideline in terms of like timing detector main effect in terms of resolution. To be fair, most of these timing detectors for HL-LHC are not really meant to be used only for particle ID. They can be used, but also meant to distinguish different interactions. So when we talk about the LHC interaction region, we talked about the Gaussianly distributed with a sigma of about 180 picosecond in time, while the timing detector we are looking at, they will have a resolution of about 50 picoseconds, which then will allow us to figure out if a particle is coming from a given proton-proton collision or another one that might overlap in space, but not in time. And this plot shows you versus Z and time, the distribution of various interaction, and then how well you can distinguish them if you use timing information, this is the 4D, or if you use just spatial information. So you basically add an extra dimension in being able to distinguish charged particle reconstructed there. 9, 10, okay, perfect. Yeah, so the red dots here are simulated interactions, and then every interaction will produce some amount of charged particles, and that amount fluctuates. So some of them will just not give us enough charged particle to reconstruct them. We actually just need 2 charged particles to reconstruct, but we've seen that the efficiency of reconstructing that charged particle depends on a minimum momentum, and also depends on if I had an hadronic interaction or not. And in fact, if I have to sort of draw, okay, the typical momentum, the majority of the charged particle interaction. So actually, let's put it this way to give you some orders of magnitude. In an elastic PP interaction will produce, let's say, as a wide distribution of how many charged particles can produce. It can range easily from the ballpark 10 to 30, let's say. Let's put it 10 to 40, okay, that type of amount. The transverse momentum, however, distribution of this particle is very low, is actually Let's say most of them will have 100 MeV, 50 MeV, 200 MeV is governed by the QCD that binds together the protons. And the charged particle we can reconstruct at the high luminosity LHC, we expect to be able to reconstruct charged particle above about 1 GeV. And so only a fraction of them have enough momentum to be reconstructed. And I need at least 2 of them to be able to reconstruct a position of an interaction. So that's why many of the red points don't have a reconstructed vertex attached to it. Yes. Yeah. Yeah, it is. It is corrected. So the time walk, it is corrected. But now remember that sort of, we don't know that charge with infinite precision. We discretize it and we know with only some accuracy. And then I have no idea within that range, what is the exact value. So my correction can only be on average. So we correct the first order, and then we have the second order effects that enter the resolution. But absolutely, those corrections need to be made, otherwise that would actually be dominant. But those corrections are made offline in terms of calibration. Yes. Okay. Okay, very good. Okay, and in fact, this timing detector, in addition to help for pileup, actually can be used for particle identification. And this is an example of like, this is another beyond standard model scenario where you have in between the 2 points that are circling red, that particle, that neutralino, that travel a macroscopic distance. And while everything else basically happens essentially in the same instantly. And so measuring the time of flight, you can actually, and with some assumption, you can even reconstruct, you can identify a particle, see if that flies with a speed slower than the speed of light. And with a little bit of assumption, the kinematic, in this specific case, you can also reconstruct the mass of that hypothetical particle. And so here, the plot on the bottom shows, depending on the time resolution, the time of flight resolution you have, how well you reconstruct that mass. And this is something that CMS is expecting to be able to do at the luminosity LHC, for instance, which is pretty nice. Okay, so as a quick wrap up of the particle identification part, I just wanted to show this thing in which essentially we have various ways to measure the momentum and velocity of the particle. We talk about the curvature in the magnetic field. It will give us is proportional to essentially our momentum. We have the ionization energy loss, which is depending on beta gamma. We can measure, of course, the energy, but the time of flight and the Cherenkov radiation. So we basically usually use a combination of those, depending on what is available, what is the correct momentum range that they apply to. But just a quick way to summarize it. And also, we often assume a unit electric charge. So if you want to relax that, you need an extra measurement to disentangle the ambiguity. Okay, there are many other, there are a few other effects on charged particle reconstruction, which I don't want to just go into for sake of time, because there's so many other things I want to talk to you about. But I just wanted to mention scintillation, since we'll see a little bit when also charged particle can excite an atom, and then the electron coming back will emit some light. And then transition radiation, which also is when a charged particle traverses a medium which is made of 2 different index of refraction, and then can cause radiation, particular pattern radiation to be released. And both of these things are actually used in current detectors at the LHC. But I will not go much into details. I just wanted to mention for completeness. Okay. So this covers a little bit the part of charged particle interaction for matter, and how we basically do these algorithms to reconstruct them. So now I want to a little bit switch gear, and I'll start introducing a little bit what about neutral particle. Not all the world is made of charged particle, unfortunately, but it's they're much easier fun. But we also have neutral particles. And so there are a few processes that govern how the neutral particles interact with matter that I think are at the basis of the way we design our detectors. And there are essentially, when talking, and let me start talking about photons in particular. When talking about photons, there are essentially three different types of processes, which are each dominant in different energy regime. You have photoelectric effect when a photon interacts with a medium, ionizes an out, and can ionize, can excite an electron that can basically go outside, go out of the bound of the atom, or can go back and then emit another photon. You can have Compton scattering when you have the scattering of a charged particle with a photon. And you can have pair production where again, you have a photon that interacts, that together with the Coulomb field of an atom can convert in an electron-positron pair, okay? And of course, this one is only kinematic allowed if the energy of the photon is greater than 2 times the mass of the electron. And the other two basically gives you just the energy of in the Compton scattering, the energy of the scattered photon depending on the angle. The important thing to remember of the Compton scattering is that the angle is directly connected with the energy of the outside photon. So if knowing the two of these three things, the angle, initial energy, and final energy, you can determine the third one, which is very useful in many applications. So the other concept in terms of like photon going through material is how much they are practically absorbed based on sort of the sum of these effects. And so the total absorption is basically can very well be described with an exponential. So you have some intensity of photon and the intensity at some depth, it will be an exponentially decreasing function with some constant. And that constant depends, of course, on the material and depends by the sum of these three effects. So practically that constant, that new constants depend on the material properties and is a sum of the probability of having each of these three effects. And each of these three effects can be parameterized, and there are approximate formulas that give you an idea of how that goes with the properties of the material. So for instance, pair production, you can see here, and again, you see this X0, which is the radiation length that comes back, is the same radiation length we defined earlier. You see the photoelectric effect and the Compton, and you see that they have different dependencies on energy and different dependencies on the material. So that already tells you that as the energy of the particle and the material properties change, which effect becomes more important will also change. And this is basically what is shown in this plot here, which as a function of the photon energy, and this is for a specific material, it gives you the probability of each of these effects happening. So what went into this sigma I, this cross section of each of these different effects. And so depending at very low energies is where you have sort of the more photoelectric effect. Then you start seeing the Compton effect that has this dependent on energy. And then at very high energy, in this case above a few, closer to a GeV, where you start having pair production as becoming the dominant effect of photon interactions. Okay, so practically speaking, photoelectric is the lower part, then Compton takes on, and pair production at very high energies is the dominant mechanism. That's sort of the rule of thumb. It's the photoelectric effect because it depends on the bonding energy of the electron in the atom. And so the probability of sort of getting interaction depends on the band gaps at the energy levels of the atoms. That's why you get this type of effects. Okay, so how do we detect these photons given this interaction mechanism practically? So the most obvious, the first sort of detector that was built is this sort of photomultipliers, where essentially you have a photon that interacts with some medium at the beginning, and then because through photoelectric effect, And then that electron gets multiplied because one electron is just too small to see. So you have a set of electric fields that make the electron bouncing around. And as it hits each stage of the material, it basically excites. So you accelerate that electron that has enough energy to excite more electrons that then go to the next stage and then keep amplifying until at the very end, you can actually read out a signal. And in fact, you can, so you have an increasing potential that keeps accelerating that electron, and then you read out a signal towards the end. You will hear the typical factor of amplification is very large, up to 10 to the 7. That is needed to have a pretty large signal to be able to read out easily. And that means also that all photomultipliers needed a very high voltage. So very often you see old photomultipliers were sort of tubes of this size long, and then they needed, I don't know, hundreds of volts, 1,000 of volts of high voltage to be able to do the amplification. And you often also see this metric we call quantum efficiency, which is essentially the efficiency of detecting a single photon that enters. Now, because the probability of interaction of photon depends on the energy, as we've seen, that efficiency depends on the material you put at the beginning. So depending on that material, you will have different efficiency depending on the energy of the photon. And that's why these quantum efficiency plots, so the probability of detecting that photon will have some dependence that depends on the energy of the photon, the wavelength of the photon. And depending on different material, you can design photomultipliers to detect different type of photons. Now, the world, especially in particle physics, has completely changed in the last 20 years or so with the advent of silicon-based photomultipliers that basically use a similar things as a silicon detector, very, very thin, and is sensitive enough that the energy released by the photon in this semiconductor produces similarly an avalanche of small electrons that can be detected. And those are very compact, they can be tiny, and they need a much smaller voltage to work. So they are very easy, they're more expensive, but they're very, very, very much used in application where space is a problem and you need many of them and you need a very good performance. And they can also work well in magnetic fields. While there, you can see if you need an electron to accelerate in a very good path, if you start putting a magnetic field, that will alter the trajectory of the electron, make it more hard to work in magnetic fields. Okay, so this is essentially these are the basic processes that go into making what we call calorimeters. And calorimeters are really the instruments that sort of have as a job to block the particle that is coming in and measure, to stop it and measure the kinetic energy that that particle had. And we usually define two types of calorimeter, what we call electromagnetic and hadronic calorimeter. And we'll see now why, but essentially this basically wants to introduce a concept of like, how does, given what we just talked about, how does a particle interact with a huge block of matter? And then if I have an electron of a photon, when it starts interacting with matter, this will be dominated by electromagnetic interactions. And so what will happen is, like in that example, is for some energy, for instance, bremsstrahlung will start dominating. So we'll start having a photon that is radiated off the electron. And that photon is a very high energetic photon. So what does it do? Primarily does pair production. It produces 2 electrons. And then each of these electrons, again, will have enough energy that will probably do bremsstrahlung very quickly. And then that photon goes to a pair of electrons. So you develop essentially a shower of electrons a photon then develops with depth. In the case of hadron, our primary interaction are these nuclear interactions. And so in a hadron that basically will hit a nucleus will create a set of other particles which themselves can hit other nuclei and then create a shower of hadrons that develops of both charged and neutral hadrons. So that will be the challenge, that will have a very big, a way more varied shower of very different of hadrons that are created with a mix of charged and neutral hadrons and different species. The electromagnetic one is a much simpler in quote shower, which develops really with these electron and photon propagation. And then sometimes you may have also muon produced in the shower, will just then have very little energy by ionization, then will exit your material block almost undetected, leaving very little energy, going against the principle of trying to stop everything and measure it. So, yeah, let me see, maybe we can, should we just stop here? I see it's almost 10:30. So that before I start going through, we can have a quick break. Yeah, and we start maybe 5 to 11, something like that. Sounds good? Okay.